All right, so I guess there were a few questions on the GroupMe chat related to the labs and the format that you need to follow for the labs. We don't require any specific format, but we have uploaded a report template for you to use. Maybe you can just go there and see. It's basically just a very standard Word template. And what is required of you for the pre-lab section is just note down the question number and then put a screenshot or maybe your calculations, whatever calculations you're doing, or if you're for the subsequent labs, if you have to put a screenshot somewhere, please do that. It's as long as it is there and if the question number is mentioned, it should be fine. Okay. So please follow a similar format. Again, for the in-lab section, it should be very similar. We don't require any specific format as long as all the screenshots are there, all your calculations are there, and the particular question number is mentioned, it should be fine. So I'll post that in the GroupMe chat as well. I saw that there were some questions. Yeah. So the same document. Yeah, you can use the same document. It's just a template. You can use the same template for both. All right. And again, labs are going to start next Monday. So please make sure you know which lab section you are in. And of course, your TAs will help you to, let's say, in some of these in-lab sections and related to the questions on the in-lab sections. All right. So in the last lecture, we saw op-amps, and we basically went over something that you already know, that if the op-amp is ideal, and if there is a feedback network, maybe something like this, then how do you find out the gain? And in this case, it was very easy. It was pretty easy to find out the gain because you knew that this is an ideal op-amp, which really means that there would be no current going into the op-amp. So if you know that this point is V in, and due to the virtual ground property that the AC voltage at this node, the positive terminal will be same as the AC voltage at the negative terminal. And in this case, it's an AC ground. So that's an AC 0 voltage. On the other hand, here you have an AC potential, let's say V in. Maybe that's a sine. Okay. So the current, the AC current that flows through this resistance R1 would be V in minus 0 divided by R1. That's the current that flows here. Now, because the op-amp is ideal, that entire current that flows through R1 will go on and flow through R2 as well, right? But as soon as the op-amp becomes non-ideal, you cannot do this, right? So whatever you learned in 3111, that's only applicable if the op-amp is ideal, right? If the op-amp has infinite input impedance, if the op-amp has zero output impedance, if the op-amp has infinite gain. So only in those scenarios, you can apply what you learned in 3111. But in reality, op-amps are non-ideal. So there would actually be some current that is going into the op-amp. And this equation that you had solved or you had found out in 3111 or even in the previous lecture, this equation is not correct whenever you think about a real op-amp. Because real op-amps, current will go in. Real op-amps will not have infinite input impedance. And they will not have infinite output impedance. And they will not have infinite gain. Okay? So how to solve in those cases? Because in reality, you'll always be given a real op-amp. In the labs, whenever you go for internship, whenever you join a company for a job, you'll always have real op-amps if you're working with op-amps, right? So how to make sure that you know how to at least analytically or theoretically solve those scenarios, that's what we're going to learn in today's lecture. Yeah. All right, and we're going to kind of create a simplified method using which you can solve any problem related to real op-amps. So for example, depending on the circuit that you have, you can always figure out how much current actually goes through that R2 resistor, how much current actually goes inside the op-amp if an input impedance is given. So all of that, I think you can already do depending on, okay, just consider it as a very complex nodal analysis problem instead of a simple nodal analysis problem, right? So you can always do that. But what I want to do in today's lecture is kind of follow a method that we want to learn a simple technique that using which you can always solve these real op-amp related problems. Okay. All right. And That method is going to be called the loop gain method, because we will be using the loop gain, the concept of loop gain, which we learned during the discussion on feedback. Okay, because you'll see that all the time we'll have a closed loop network with an op amp, so we'll always have a feedback, because an open loop op amp is not very useful. It has very high gain. It will just saturate your outputs. It's not very useful in most of the real scenarios unless you want that. Okay. Um, so using this loop gain method, what we are going to do is that you already know the equation for feedback, right? So the equation for feedback, let me write that down, is, let me use a different color. So the equation for feedback is A divided by 1 plus A beta. And with op amps, you'll always be dealing with some kind of a feedback, because again, open loop op amps are not very useful. They'll just saturate your outputs. So, and all the circuits that you learned in E-Circuits1 with op amps, if you think about it, everything has a closed loop feedback. There was always some resistor, some capacitor, some inductor going from output to input, right? So you'll always have some kind of a feedback. And you already learned that the equation for feedback is A divided by 1 plus A beta, if this is a negative feedback. Again, we are only considering negative feedback for now. In a more general case, you can also consider positive feedback. Okay, so this was the equation that we learned in class, that if A is your feed forward gain, maybe let me draw it here. If A is your feed forward gain and beta is the gain of your feedback network, and you have a negative feedback, which means that you'll be subtracting the feedback quantity from the original input quantity. So that's what you have. So this is the transfer function for this entire feedback network. Now, if I divide my numerator and denominator with A beta, let's say I divide both my numerator and denominator with A beta, so you can write the same thing as 1 upon beta divided by 1 over A beta plus 1. Okay, so I just divided my numerator and denominator with A times beta. Very simple mathematical operation. Now think about it. What we basically discussed during when we were discussing ideal op amps as well as feedback, that A is the gain of your feedback path. And remember that if A is very, very high, that is when you have an ideal op amp with infinite gain. So let's say A is infinite. Then this A divided by 1 plus A beta, that just becomes 1 upon beta. So let me also write that down, that if A is tending towards infinity, then this quantity becomes just 1 over beta. Why? Because you can divide your numerator and denominator with A. So on the numerator, you'll have 1. In the denominator, you have 1 upon A plus beta. Now, you already know that A is tending towards infinity. So 1 upon A will be almost equal to 0. So you can just ignore this part. So what you're left with is just 1 over beta. That's the overall network's gain, the gain of the feedback network with the feedback, if A is tending toward infinity. Now, when does A tend toward infinity? If you have an ideal op amp, if your feed forward path's gain A is coming from an op amp, and if that op amp is ideal, you know that the ideal op amp's property is that the gain is infinity, right? So if you're using an ideal op amp with an infinite gain, your gain of the closed loop network becomes 1 over beta, because it's just A divided by 1 plus A beta. And we did this mathematical manipulation for A equal to infinity. And then we ended up with 1 over beta, right? Now, interestingly, in this equation, 1 over beta is in the numerator, right? If you had divided both numerator and denominator with A beta, you would have gotten 1 over beta in the numerator, which is shown here on the top. And in the denominator, you have 1 plus 1 over A times beta. Now, remember when we talked about loop gain, we said something interesting, that if you open up the loop, if you, let's say this is a closed loop network, right? So let's say you open it up. You do not have a closed loop anymore. So let's say you open somewhere over here, for example, and then consider the gain in the entire network. So that will just be A times beta, right? The loop gain is just a multiplication of the gains of the individual components in the network. So the loop gain is A times beta, which is over here. and you have a 1 over beta, which is the gain of the closed loop system, if you had assumed an infinite feed forward path gain. Okay. So this equation you can represent as A infinite divided by 1 plus 1 over t. Now, what is A infinite? A infinite is the overall system's gain if you had assumed an infinite feed forward path. So if your feed forward path's gain A is infinitely large, then your feedback becomes A divided by 1 plus A beta, and that boils down to 1 over beta if A is infinitely large. That 1 over beta is something that you have at the numerator, right? So let's call that A infinite. So A infinite is nothing but the gain of the system if you have A equal to infinity. That's what it means. A subscript infinity. That means if A were infinity, what would have been the gain of the entire system? Right? That's in your numerator. In your denominator, you have 1 plus 1 over t. So you have 1 plus 1 over t. What does t mean in that case? T means the loop gain. So t is equal to A times beta. Right? So as you see, A infinity is the gain of the system when A is tending toward infinity. In that case, the loop gain will also tend toward infinity. However, in the real system, the loop gain will not be infinitely high, right? Also, the feed-forward path gain will not be infinitely high. So as you see that it might seem a very simple mathematical manipulation, just that, right? It's nothing more than that. So why is it interesting and why is it important? So if you think about a real op-amp or a circuit with real op-amps, in that case, if you're asked to find out the overall gain with, let's say, non-infinite or finite input impedance, non-zero output impedance, and so on. We'll look at an example and it will become very clear. First, you consider the scenario when you have an ideal op-amp and find out the gain for the ideal op-amp. That's your A infinity. Just consider you have an ideal op-amp. So your gain is infinitely large, your input impedance is infinitely large, output impedance is 0. Find out the gain. That could be very simple, something like, so for example, if you have a non-inverting op-amp, which is shown over here, right? So you apply your input to the non-inverting terminal of the op-amp, and then you have a feedback network containing R2 and R1 over here, and that goes back to your inverting terminal of the op-amp. So this is a negative feedback, and you already know how to solve this. You have solved this in 3111. You have also solved this in the previous lecture. You know that the gain would be 1 plus R2 over R1. But this gain, 1 plus R2 over R1, this is assuming that this is an ideal op-amp. We never assume any non-ideal. So this A infinity is nothing but 1 plus R2 over R1 for this scenario. Right? So now you have segregated ideal op-amps and non-ideal op-amps. Your numerator is just ideal op-amp in this equation. A infinity is just what you get with ideal op-amps. In your denominator, you'll have 1 plus 1 over t. And that loop gain t, which is nothing but A times beta, that will have a contribution from your feedback network. So for example, this one, R2 and R1, you're creating a feedback network, that's the beta. But the A, or basically when you find out the overall loop gain, you will consider all the non-idealities. For example, the non-ideal input impedance or the non-ideal output impedance of the op-amp. So all those non-idealities will come inside this T, inside this loop gain factor. So that's the method we are going to apply, that your numerator, ideal op-amp, your denominator, you look into the non-idealities. And that will make your analysis really simple, as you'll see in the example in the next slide or the next page. Okay. So what kind of non-idealities are we talking about? If you look into this right-hand side figure, this picture, you'll see that you have this Vs input voltage source, and you have this current coming in. Now, if the op-amp does not have an infinite input impedance, let's say it has a finite input impedance of Ri. So R, which stands for resistance, I stands for input. So input resistance of Ri. So of course, now you will have a current path, right, through this. And then you have this A times Vi at the output side. You can also have a non-zero output impedance for the op-amp. So you can consider that as, let's say, Ro. And then that is fed back using this resistance R2, which is over here, and you have this R1. So you have a voltage division between R2 and R1 over here. And some part of that voltage goes back here, which is also connected to the bottom terminal of this Ri input resistance, right? So you see that that becomes your overall network with the non-ideal op amp. Now, to find out the gain of this non-ideal op amp, you can just solve KCL, KVL, do your nodal analysis, and you will come up with the same answer. Again, there are multiple ways to come up with the correct answer in circuits. But here, we are just trying to make sure that we follow a method. So, and that method will tell you that first consider an ideal op amp. So, find out what is your A infinity, and A infinity will be 1 plus R2 over R1. Then you divide that by 1 plus 1 over T, and inside T, consider the effects of Ri and possibly Ro as well. Okay, so let's take a look at that example in the next page. All right. So what you're trying to do is basically finding out the loop gain T, because finding out A infinity is probably easy. You can all of you, I'm assuming, can do it because all of you have gone through 3111. So A infinity is that easy part, what you learned in 3111. Finding out T is the new thing that you're learning in this course. Okay, so let's take an example where again you have this input source, you have a resistance R3 connected to the positive terminal of the op amp, you have your output of the op amp, then you have a feedback network containing R1, R2, and R4. Okay, and you're feeding back a part of that voltage back into the negative terminal of the op amp. Now, if you draw the internal circuitry of the op amp, which will be this. So this is your internal circuitry of the op amp. You have an input impedance of Ri. Okay. In a real scenario, you'll have an input impedance of Ri. You have A times Vd. So whatever voltage that you develop across Ri, that's the voltage at your input of the op amp. Right? What is the job of the op amp? The job of the op amp is to amplify the voltage that is available between its positive and negative terminals. Right? Yes, question. Could you please repeat the question?
What should get rid of VS?
Oh, okay, all right. We'll go into that. So that's a very good observation that we got rid of VS for the right side diagram. So we'll go into that. But first, think about the op amp, that you have this dependent voltage source, and the dependent voltage source's value is A times Vd. Remember that it should not be A times Vs, because as soon as the op amp becomes non-ideal, you have a resistance over here. So you have voltage divisions between R3, whatever resistance you have at the input of the op amp, and the other resistances connected in the circuit, right? So the output of the op amp is not A multiplied with Vs, because this is a real op amp. This is not an ideal op amp anymore. So your output of the op amp, or basically this dependent voltage source, is going to be A times Vd. And Vd is the differential voltage. That is the difference of voltages at the top terminal and the bottom terminal of Ri, which are basically the positive and the negative terminal of the op amp. Okay? So that's very important to remember, that the op amp's job is to amplify this difference voltage. The job of the op amp is not to amplify the voltage over here. Whatever voltage that you see at the input of the op amp, that's what it is going to amplify. Okay. Now, a very interesting question and a great observation, that on the right-hand side, we are getting rid of the source Vs. Because on the right-hand side, what we'd like to find out is the loop gain. And what is the loop gain? It's the multiplication of all the gains that are there in the system. Now, of course, for this dependent voltage source, you already know that there is a gain of, let me draw it with a different color. You already know that there is a gain of A. Right? That's the gain of the op amp. It could be some finite value, let's say 50 or 100 or 10,000. So there is a finite value for this gain. However, there would be a beta network. You know that what is your loop gain T? Your loop gain T is A times beta. Right? A is the gain of the op amp, and beta is the overall gain coming out from all the voltage divisions that are happening in the circuit. Right? So now our job is to find out beta. And if you're trying to find out beta, you're basically looking at a resistance network, right? You're effectively trying to find out what is the effective Thevenin resistances. And you know that when you're trying to find out Thevenin resistances, you get rid of all the independent voltage sources. And that is the reason why on the right-hand side figure, you have gotten rid of this independent voltage source Vs. Because eventually what we want to find out, that what is the loop gain? And that loop gain only has two components. One is A and one is beta. And none of that requires a voltage source, right? An independent voltage source is not required to find out A or find out beta. A is given and beta is something that you'll find out. Okay. So how do you find out beta? So if you look into here, this T is your loop gain. That is going to be A multiplied with beta. And beta is this complex resistive division. But it may look complex, but you have already looked into voltage divisions in your homework 1 or in the first few lectures of this course, right? So we'll be using the same approach, the same formula and everything. But it's just that it's a more complex problem. All right. So how do you find out beta? So to find out beta, you can start from any point in the circuit. However, it's easier if you start from, let's say, the output of this voltage source, this dependent voltage source, and try to traverse the entire circuit to eventually find out how much of the voltage is getting. So this is the output of this dependent voltage source, right? So how much of that output voltage from the dependent voltage source is getting feedback at the input of the op-amp, that is in between these two terminals, the positive terminal and the negative terminal over here, the top and bottom terminal of Ri. How much of the output voltage is getting transferred back using the feedback network? That's what you're going to find, and that's your beta factor. So to do that, what is connected right after the dependent voltage source? You have RO, the output resistance of the dependent voltage source. And then you have a complex network of resistances. To simplify things, let's just assume that the complex resistive network that is connected after RO is called RY, R subscript Y. Okay, let's just assume that everything that is connected after RO is R subscript Y, the equivalent resistance. So if that is the case, you basically have this dependent voltage source, okay, and you have RO connected at the output of it, and then RY connected after that. So RO is connected here, and RY is everything, the equivalent value of the resistance for everything that is connected after R. So this is a very simple voltage division. Now you want to find out, let's say, what is the voltage that is now available across RY? That's a very simple voltage division. That's RY divided by RY plus RD. That's the first component that you see here in beta. Okay. Okay, so now we know how much voltage is developed across RY. Let's traverse the network further. At this point, you have two parallel paths. One goes towards left side and the other one goes to ground. You know that if there are two parallel paths, the voltage, the current can get divided, but voltage does not get divided. You have the same voltage across both of the paths. So if your voltage at this point is Vy, like at this point, if the voltage is Vy, that same voltage is over here, Vy, that Vi voltage drop is happening across R4, but Vi voltage drop is happening across all the other resistances on the left side as well, right? So R4 is not important. That means if you want to find out what is happening here, what is the voltage drop that you get across the input resistance of the op-amp? So you'll only be looking into whatever is happening on this left side, and then there will be further voltage divisions happening across these resistors, but R4 is not important because R4 has the same voltage drop Vy, but it's not important if you're trying to calculate the voltage drop across the input resistance, right? So that's why you look into the left side and try to see what you find. So let me clear this up a little bit. All right, so if you look into the left side from R4, you'll see R2 resistor, that's a resistance in series. And then you'll again see a complex network of resistor over here. So let's simplify our lives. Let's assume that this complex network of resistor is going to be called Rx. So whatever you see on this side looking toward left from R2 is going to be called Rx. So now again, you have a very simple voltage division between R2 and Rx. You're interested in the voltages that eventually get developed across Ri, which is part of Rx. So that's why you'll be interested in the voltage drop across Rx. And that voltage division ratio will be Rx divided by Rx plus R2. That's the second term over here. So now you're at this point, right? Whatever voltages are developed here. Again, you see that there are two parallel paths. Current can go through R1, current can also go through this path. But because you're interested in the voltage developed across here, you're not interested in whatever happens in the R1 path. So that's why you see in the beta network, there is no mention of R1, there is no mention of R4 because those were not important. Okay, so if you're interested in what happens in this path, again, as you see that whatever voltage gets developed here, that would be divided into two parts. One voltage drop will happen across Ri and another voltage drop will happen across R3. And remember the left side of R3, because we are getting rid of this Vs, the original voltage source, you're basically shorting this left part of R3 to ground. That's why you see this ground connected to the left part of R3. So the voltage gets divided into two parts, one across Ri and the other one across R3. Which one are you interested in? You're interested in the voltage drop across Ri because that's the input voltage that you see at the op amp. So basically that's the amount of voltage that is fed back from the output to the input side. Whatever voltage that gets developed across Ri, that's the input voltage that gets fed back from the output side. Correct? So you're only interested in that. And what is the ratio? If you have Ri and R3, the ratio that you're interested in is Ri divided by Ri plus R3. So that's the third term. So your overall beta network becomes Ry divided by Ry plus Ro, where Ry is this resistance that you see looking on this side. Then you have another division Rx divided by Rx plus R2, where Rx is the resistance, complex resistance looking this side. And then finally, you have a voltage division between Ri and R3. Those are all the voltage divisions that you see. So think about it. It's in its core, it's nothing but your homework problem 1, 2, 3. It's just that the problem is a little bit more complex. Okay, so what is Rx? Rx. So now that you have represented beta in terms of Rx and Ry, you also need to find out what is Rx and Ry. So Ry, if you think about it, Ry is R4 in parallel with R2 plus Rx. So if you try to find out what is Ry is R4 because this path is going to ground. And on this side, you have R2 in series with Rx. So you have R4 in parallel with R2 plus Rx. That's what you have as Ry. Similarly, what do you have as Rx? Rx is going to be the resistance that you see looking on the left side at this particular terminal, this particular node. So here you have R1, and the current gets divided into the other path and flows through Ri plus R3. So Rx is going to be R1 in parallel with Ri plus R3. So now you know what is beta as a function of Rx and Ry. You also found out Rx and Ry as a function of R1, R2, R3, R4, all these resistances, right? So you have the entire solution here. So you can find out what is T, that is A times beta. And if you go back to the previous page, where you wanted to find out the overall gain of the system, if this is a non-ideal op amp, that's going to be the gain of the system. If it were an ideal op amp, that's in the numerator, divided by 1 plus 1 over T, where T is the loop gain that you just calculated. That's A times beta. And all you needed to do was to calculate beta, keeping in mind that there is a finite input impedance and a non-zero output impedance. Okay. All right. Now think about this. Let's say if you, let's say if your output impedance of the op amp is 0. So let's say Ro is equal to 0. And let's say the input impedance of the op amp is infinitely large. So Ri is infinite. Okay. So what would happen to your beta network? Your Ry divided by Ry plus Ro, that term will go away because Ro is equal to 0, right? Because Ro is equal to 0, this becomes Ry divided by Ry, which is equal to 1. So there's no need for this term. If your input impedance of the op-amp is infinitely large, then Ri divided by Ri plus R3, that also goes away because Ri is infinitely large. R3 is of course a finite value. And again, you have Ri in the denominator as well. So this term is also equal to 1. So this will also go away. What you are left with is just Rx divided by Rx plus R2. Now what is Rx? Rx is R1 in parallel with Ri plus R3. Now you already know Ri is infinitely large. So putting anything in parallel to something that is infinitely large will mean that you just have this original quantity on the left side, which is R1. So Rx will become equal to R1. Okay, Rx will be equal to R1. So you have Rx is equal to R1. And your beta, the feedback network, is just R1 divided by, oh, sorry, this is R1. So your feedback network becomes just R1 divided by R1 plus R2. Right? So as you see that if the op-amp were ideal, you would have a very simple network. So let's just put that over here. So let me write that down here. Beta is going to be your R1 divided by R1 plus R2. If the op-amp were ideal. A is something that you already know. That's the op-amp's gain. A infinity divided by 1 plus 1 over T. Now, if you just put the values, your A infinity in this particular case is let me clear this up a little bit. So A infinity in this particular case is when you assume the op-amp to be ideal and you already know that is going to be 1 plus R2 over R1. So your A infinity is 1 plus R2 over R1. Okay. And your 1 plus 1 over T, that is just 1 plus 1 over A times beta. And A times beta is just A times R1 divided by R1 plus R2. Now, if you simplify this equation, what should you expect? Because we are taking an ideal op-amp and putting it back in this A infinity divided by 1 plus 1 over T equation, we should get the gain of the ideal op-amp. So this complex equation should boil down to 1 plus R2 over R1 eventually. And let's see if it does that. So you have 1 plus R2 over R1, and in the denominator, you will have what? You'll have 1 plus R1 plus R2 divided by A times R1. And here you will have R1 divided by, and in the numerator you will have R1 plus R2. So now if you simplify this, if you simplify all of this, this will become A R1 times R1 plus R2 divided by R1 times A R1 plus R1 plus R2. Now, if you have your A to be infinitely large, of course, you can divide your numerator and denominator with A in that case. And in the numerator, you'll be having R1 times R1 plus R2. And in the denominator, you're going to have R1 times AR1 divided by A, that is going to be just R1. And R1 divided by A and R2 divided by A, that will be 0. So R1 plus 0 plus 0. So eventually what you end up with is your R1 gets cancelled out and you have 1 plus R2 over R1, which was the original equation for your ideal op-amp. So what we just did, I mean, it may sound circular, but what we just did is started with the non-ideal op-amps equation, which is A infinity divided by 1 plus 1 over t, and then put the values accordingly to the ideal op-amp and showed that eventually the gain is equal to the gain of the ideal op-amp, which is 1 plus R2 over R1. Question?
I get where the numerator came from. It's 1 over beta.
Yeah.
Okay, so can you explain where the t in the whatever t came from?
So numerator of what? Numerator of this equation?
1 to the right of it.
To the right of it?
Yeah. Where did you get when you plugged
Yeah,
in?
perfect. So you saw what beta looks like. Beta is equal to R1 divided by R1 plus R2 if this is an ideal op-amp, because in that case your input impedance becomes infinity, output impedance becomes 0. So that's what we calculated in the next page, right? So out of the 3 terms, 2 of them becomes 1 and you're only left with the middle one. So that's your beta. And t is equal to what? T is equal to A times beta. So 1 over t, that's basically 1 over A times beta. So A is this and beta is R1 divided by R1 plus R2, which is calculated here.
Oh, so the non-ideal op-amp was just an ideal op-amp.
So here I'm trying to show that for the non-ideal op-amps equation, which seems like a complex, very large value. So again, let me just go back to the next slide. So as you see that you calculated beta, which looks like a very complex equation of resistors and so on. But this is a more general form of the equation. Now, if you assume certain things that, okay, if my Ri is infinite and if my Ro is 0, then all that complex equation boils down to 1 plus R2 over R1, which is the case for the ideal op-amp anyway. Right? That's what I wanted to show. That start from the general equation. The general equation is A infinity divided by 1 plus 1 over t. That's a more general equation, that you have your numerator as ideal op-amp. In the denominator, you have all the non-idealities incorporated. Now, if you get rid of the non-idealities, this equation will be same as the 1 plus R2 over R1 equation, which was the case for the ideal op-amp. So you can think of all of this as just a generalization of whatever you learned in 311. In 311, you learned about just A infinity. We did not learn about loop gain, or we did not learn about the denominator at all for this particular equation. In 311, we only learned about the numerator, and the numerator is for ideal op-amps. If you want to consider the non-idealities of the op-amps, you have to calculate T. And T is A times beta, and we just saw an example of how to calculate beta. Here is another example. Now that you have gone through the first example, this should be easier. But here, the only trick I have here is that instead of using a dependent voltage source, we are using a dependent current source. Right? So, and you know, MOSFETs are current-controlled current sources, right? Or sorry, MOSFETs are voltage-controlled current sources, and BJTs are current-controlled current sources. So in reality, BJTs and MOSFETs will be represented as a current source, right? A dependent current source, and the value of the dependent current source is transconductance G times whatever voltage you have at the input. So again, whatever voltage you develop across the Ri resistance. So G times the voltage developed across the Ri resistance, that would be your current at the output of the model over here. And as you know that any current source should have a non-ideal parallel resistance. And that non-ideal parallel resistance, in the ideal scenario, it would have been infinitely large. But in a real scenario, RO will not be infinitely large because this is the parallel resistance to a current source, which will be finite value in the real scenario. Okay, so how do you solve beta in this case? And what is your T? What is your overall T going to be? All right. So first of all, if you know that your transconductance is G, and G is equal and G times VD is the current over here. So whatever resistance that you see, let me just clear everything. Whatever resistance that you see at the output of this dependent current source, let's call that RL equivalent. So whatever resistance you see is RL equivalent. So what will be the voltage at this node? The voltage at this node is going to be the current multiplied with the resistance. Again, Ohm's law. What is the current? Current is G times VD. The transconductance times the input voltage of the op-amp. what is the resistance that you see at this node? The resistance looking on the right side is equal to RL equivalent. So G times V times RL equivalent is basically the voltage at this node. And what is the voltage at the input terminal of the op amp? That is VD. Right? So that VD, so whatever voltage you have at this point, that VD gets translated into G times VD times RL equivalent voltage at this point. So now you have represented your current, which was G times VD, as an equivalent voltage at this node. So you can start from that equivalent voltage directly. Okay? So you have an equivalent voltage, which is G times VD times RL equivalent. And how much of that voltage gets fed back as VD at the input node? If you find that out, that's going to be your beta. So in the previous case, the voltage was, let me go back a little bit. In the previous case, the voltage was A times VD at the output. You wanted to find out how much of that voltage goes back at the input side as VD. So here you already started with a voltage which is G times VD times RL equivalent, and then you want to find out how much of that goes back at the input side. So you apply a similar method. Again, think about this, that if this point's voltage is known, so which will be, let's say, G times RL equivalent times VD, and of course, because you're looking at gains now, that VD term, the original voltage, is something that always goes back in the numerator side, or goes back in the left side and the denominator side. So of course, if you just look at the voltage gain, then it is G times RL equivalent, right? From VD to this particular node. Now here, you have a resistance connected in parallel to ground. So again, that will not matter if you're trying to look at voltage divisions, because voltage does not get divided into parallel resistances, current does. And because you have converted your current into a voltage, now this resistance does not matter anymore. Again, at this point, you have another resistance connected to ground, R4. That should also not matter anymore, because again, you have another parallel path on this side, which you are interested in. So on this side, you just have this Rx, and you have R2 in series. So of course, you'll see a voltage division Rx divided by Rx plus R2. And then you'll see at this node, there will be one path going to ground and another path going here, again to ground. And you'll have a voltage division between R3 and Ri, between these two resistors. So Ri divided by Ri plus R3. That's going to be the voltage division term here. Now, what is Rx? Rx is the resistance that you see looking into the left side at this point. So that's going to be R1 in parallel with Ri plus R3. So R1, which is here, in parallel with Ri plus R3. That's going to be your Rx. What is RL equivalent? RL equivalent is the resistance looking here, right? So that's going to be RO in parallel with R4 in parallel with R2 plus Rx. So again, as you see, we took a very simple approach. Just look at the resistors, just look at the way the currents and voltages are getting divided, and you come up with your beta network. All right. So I'll post a homework 2 today, which will contain problems where you need to find out the loop gain, basically the beta, and multiply it with the original gain A to get the overall loop gain A times beta. Questions?
So the first answer, G times R,
right.
Why don't we account for R0?
That's a good question. So in the previous case, we had accounted for R0, right? In the first problem, we had accounted for R0. What is the biggest difference between the first and the second problem? The biggest difference between these two problems is that, let me see if I can zoom out a little bit so that I have both the figures in the on the screen. So in the first problem, you had a voltage source and you had a series non-ideality of the voltage source. In the second problem, you have a current source and you have a parallel non-ideality of the current source. However, if you're looking at the voltage divisions starting from this node and tracing your way back into whatever voltage is available at the input of the network, right? That's your beta. That's the amount of feedback that you have. Start from the output, trace your way back to the input, find out how much voltage you have at the input, right? So if you do that, in the first scenario, there was the series resistance and then there was something connected after that, right? and voltages get divided if there are two series resistances. So in the first case, in the first example, you had the effect of R0 or RO because it was a voltage division between two series resistors. Whatever the two series resistors, one was RO and the other one was RY. And RY is the complex resistance that you see looking down at this point, but let's just assume that everything was RY. So you had a voltage division between two series resistors. In this case, you first found out what is the equivalent voltage at this node. That equivalent voltage at this node is G times RL equivalent times your VD, basically this voltage across your RE, right? So you found out the voltage at this point, and then you try to trace back. You apply the same method. It's nothing different. You try to trace back toward the input side, try to find out how much of the output voltage is available at the input. Okay? But while doing so, the first thing that you encountered here is this parallel resistance R. In the previous case, you had a series resistance R. Voltages do not get divided if you have a parallel resistance. That's the only reason why you do not see a voltage division term with R in the second case. Right? However, there is still an effect of R. We are not saying that RO has no effect at all. Why do we say RO has an effect? Look at the equation for RL equivalent. So you had a voltage of G times RL equivalent, right? What is the equation for RL equivalent? That is RO in parallel with R4 in parallel with R2 plus Rx. So RO has an effect. It's just that it's hidden inside this RL equivalent. But you'll not see in the voltage division term because the voltage division does not happen across RL. Okay, I hope that answers the question. Yeah. Any other question here? I wanted to take time and solve or go through these two problems because this is going to be very important for all the subsequent analysis and also for homework 2 questions.
So I have to like solve it twice, one and then the T, but can you just solve it with T and plug in the ideal op-amp assumption? You like in twice such twice.
You can do that, of course. I mean, that's again, as I said, there are multiple ways to solve a circuit problem. It's just that the first part, the A infinity, is something that you're already familiar with. You learned that in 311. So I don't want to play around with that. Whatever you learned in 311, that stays, but that stays in the numerator. In the denominator, we are learning new things and we are finding out how to figure out beta and how to plug that in the equation to find out the overall gain for the real op-amp. But again, if you want to follow other methods, that's also fine, whatever works for you. But this is a method that I think will be useful for almost everyone. That, okay, you just segregate what you learned in 311 and what we are learning now. Yeah. So I'll post the homework problem, but the homework problem will also, it will ask to find out what is T, what is the loop gain, but it will also try to find out what is the input and output impedances, which we are going to discuss in the next class.
Quick question.